Yeah, so last time we considered families of subsets where this was forbidden. And another trivial, self-clear property if we forbid disjoint pairs of subsets. So today I will speak mostly about this property. So this is not the famous Erdős-Corrado theorem, if you know it, but it was in the same paper, that if you have, I should have intersecting F is an intersecting family, I better write it more clearly. So it's a subfamily of all subsets now, which means that if F and G are in the family, then the intersection is non-empty. And the theorem claims that this cannot be more than 2 to the n minus first power. So this is sharp. If you fix one point and take all subsets containing this point, then it means that this is the same everyone. So you have subsets from an n minus 1 element set. This is the number of n minus 1 element sets. So you have this many sets in this family. But there is another important construction. If you take first n is odd, take all the sets which have size at least this much. So if you take two sets of this size, then they all together they have m plus 1 elements, so it cannot be placed in an element. And if they are bigger, then even more. It is true that this is intersecting. And of course this has also, because 2 to the n is the total size of all sets, and this is exactly half of it. If n is even, then we have to modify this a little bit. So we take everything above n over n half plus 1, but this is too little. We must take half of them in this level, so n half element sets. Then it's obvious that it will be again this size, because this is half of this level, and this is the same as this. So we only have to ensure that they are intersecting. So the ones from here are always intersecting. If you take an n-half element and this one, they are still intersecting. So the only point is that these must be intersecting. It's not automatic because they have n-half elements, both, so they could be disjoint. So here we fix a point and take all n-half element sets containing this fixed point. So it's similar to this case. So all n-half element sets containing this point, it's obvious that this will be, the number will be half of, because it is n minus 1 choose n half minus 1, their number, and I claim that this is 1/2 of n choose n half. Why? In the Pascal triangle, on this level, n minus 1, n minus 1, n half minus 1, and n half. If you take the sum is n minus 1, so they are equal. So these binomial coefficients sitting here are equal, and their sum is on the nth level and n half. So this will be n choose n half, right? And so it means that this is half of this. Yeah, now proof is rather trivial. I write it here. Of the inequality. If you take any set and its complement, then they cannot be both cannot be in the family because they are disjoint. So you make pairs, complementing pairs. That will be 2 to the n minus 1, and you can choose only one of each, so you cannot have more. But there is so there are many constructions. So for other investigations, this is good to know, and this is also good to know. But there are infinitely non-isomorphic constructions, and they have a very interesting property that it's a remark by in this paper that if f is intersecting, it can be extended. So you add some other sets. You can add sets in such a way that this family has n minus 1. So no matter how you start, you add disjoint sets, and it cannot happen that you must be stopped before that number. Usually this kind of theorems are not true, only in this case. Yeah, the situation is, I erase things because I need place. So situation is very different if we fix the sizes. So we consider only k element subsets. Yeah, I shouldn't have erased this one because this example is important also here. So now F is a subfamily of all k element subsets. Intersecting then F is less than equal to I deliberately missing one condition. Give me a counterexample. Sorry?
K is not 0.
What is not 0? I don't have, this is a letter?
K.
K. No. Of course, it makes no sense. If, so you cannot have a, even the empty set is not an intersect. If you have only the empty set, is not an intersecting family because but the size does matter.
Is k smaller than m divided by n? If k is smaller than half of m?
Yeah. So this is the condition, because if you have big sets, so 2k is more than n, then you cannot put them disjointly into n elements. So if you have big set, then the rest is too small. So other k element set must intersect it. So if k is more, then the problem is not interesting. You can choose all k element sets. I suppose you know the name of Erdős. Ko was a Chinese from Sichuan, and he was in England in 1938. Rado, this is a Hungarian name, but he grew up in Germany and became a British mathematician, didn't speak any Hungarian word. But what is funny, that they did this result in 1938, and they thought that this is a nice thing, but no one is interested in, because combinatorics didn't exist that time, and so Sperner started his work in number theory, and this didn't have a relevance in number theory, so they didn't publish until 1961. And so now I will give the original proof modified by Peter Frankl. We start with a lemma. No, a definition before the lemma, because I cannot state the lemma. So let x and y elements points in the whole thing, and tau x y of a set. So now k elements set, but in the definition is not important. Now is simply delete x and add y. It's not a correct notation, but you understand what I mean. So so this is f, and then this is x, y, and you take it out and add this one. Of course, you can do this only if x is in f and y is not in f. Now, we apply this transformation for a family. Again, of course, in all this proof, it will be always k element sets. Then it will consist of kind of two parts. First, we take all so we do this with every such set which contains x and does not contain y, except when this set is already there. And then we cannot move it because then it will be doubled. So, okay, so f is in the family, and is not in the family. So we apply this transformation, this trivial looking transformation for every set except every such set, except when we would get another member which is already there. And oh yeah, I was yeah. What happens if this does not hold? So f is if either x is not in f, or y is in F, so when these are not true, or tau x y f is in the family. Yeah, correction. This should be script f here, family. So, is it clear that we keep all sets which do not satisfy these properties? We move the other ones satisfying the property, except when it is already there, then we cannot move it. And so now this is the lemma. If f is intersecting, then tau xy f is also intersecting. I think I better show the proof by a picture drawing instead of making it formal. So later we will order the elements anyway. So this is why I write now. Oh no, so it's 1 to n. So these are the elements of the set, and this is yeah. No, I don't need. Do I need? Yeah, it's better to do. Okay. So this is useful, but here it will be too messy. So I denote only x and y because these will be moving. So we do this with a set like that, which contains x, does not contain y. We add this, and otherwise we don't do, and if both are there, we don't do anything with them. So how can it happen that after the transformation they are disjoint? So we make this transformation with the sets, and the two sets are intersecting, but after the transformation they are not intersecting. So there are two kinds of sets which are moved and which are not moved. So if they are not moved, both that f and g, not moved, then which are the unmoved members which contain x? So then both of them contain x. So it's not a counterexample. They are not disjoint. If f and g both are moved, this can happen only in the case when again, in this case, when, but then f prime is the f minus x plus y, g prime is g minus x plus y, and then f prime contains, now both contain y, because we moved both of them, and the modified members will contain y. So the only interesting case, so these are trivial, only interesting case when one is moved, the other is not. So f, we have f here, is moved, so it must satisfy these two conditions. So x is in f, y is not in f. And g is not, I'm sorry, I didn't write which one. So f is moved and g is not. So from f we get this f prime, which looks like this. And g is moved, is not moved. So there are several ways why it is not moved. That if doesn't hold, so if y is in, okay, so when g is either either g contains y. If it contains y, then the moved family or moved set again contains y, and g, we didn't move g, it still contains y. So then contains y. Or so if it does not contain f but contains x, so g does not contain y but g contains x. I'm sorry, no. What did I say? Yeah, so the first case was when this didn't hold. If this holds, and yeah, so one more case. when So what are the possible cases? Oh, it was too bad. So x and y, and so about f. Oh, I just show now g. So g, if it contains or it does not contain x in both cases. So when it contains y, then the resulting set, which was the original one, contains y, and then we have this case. So what else can happen? So if it contains, so this is G, contains both of them, yeah, neither one. So F does not contain Y, or G, this is G, I'm sorry, G. G does not contain X and does not contain Y. So this is the reason why it is unmoved. But then there is no change. So then the intersection of F and F prime G prime, which is equal to G, so they must, G must intersect somewhere else. If it's not in X, we didn't move this intersection, so it becomes the same. And I am sorry to continue here. This is the most interesting case. When G, X is in G, Y is not in G, but we still didn't move. Why we didn't move it? Because of this here. So that we didn't move it because it was already there, other set. G star equals G minus X plus 1 is in F. So now this in this picture. So then both of them contain X, so this is G. Both of them contain X and do not contain Y. So what happens with G? We want to do this. So this is G star. That we try to from G. We try to delete this one and add this one. So, but we cannot do it because G star is over there. So now consider F, or the original F, not the F prime, and G star. They are both in the family. So because it must be in the family, because this is why we couldn't move G. So G is in the family, and this one, I mean the original F, I erased F already, but so F, this is F prime, so I do it back. So this is F. Again, the intersection of G star and F must be somewhere neither in X nor in Y. So the intersection is the same as the intersection of before we moved. So G and F. So F clear, yeah. So because these are not, we made some changes only in X and Y, otherwise not, and they cannot meet here. So they have to meet somewhere else. So the intersection is the same. If this was not empty, then it cannot be empty either. So this lemma was the crucial idea of their proof, and this is another very nice example of this. I call it transformation method. That we make a transformation on the family, and yes, on Monday we show that the transformation is increasing the family. Here, it's he is not increasing, but so claim tau x y f is a family of k element set. Lemma says this intersecting, and the size is the same. So we have the same number of sets. So we want to take the largest family. It is still possible to look after among those which went under this operation, transformation. Now, so now it becomes important that they are ordered, so they are integers, say from 1 to n. And so we do the transformation only from a big one to a smaller one. And it will be always intersecting and same size, k element sets. So we will arrive somewhere. Will we? Because it can happen that an infinite cycle, so we come back and go back and oh, do you have a suggestion if why it has to be finished after some steps?
Because we don't move something that is
Sorry?
we don't move something
Because
it is already in family. It was moved.
I don't hear it, I don't understand.
We
So,
don't move something that were moved before in previous
it's not so clear if you I have a much more clear reasoning. So it's probably true what you say, but
because we always decrease this x for small.
yes, but still, it's not clear that we have a new family, and then you move here to this. So what happens? So basically, this is the reason that we always go down. But this can be formulated the following way: that if you take if you take the sum of the elements as now they are integers. So for every set you add up these numbers. And then you take this for the whole family. Then a transformation will make it smaller, because x is replaced by a smaller one. Nothing else happens. Yeah, in some, only in some members, but it must be smaller if we moved anything. And so this will be so it's always smaller than we must stop, because it cannot be negative. Actually, you can find a better bound, but it doesn't matter. So it will stop. And then what happens? We try to apply the transformation, and nothing happens. So when it is stopped, this is called shifted. Family. And then what is its property? So its property is that the transformation is not visible. This holds. We should denote it somehow. So this is hat. So we arrive to a family, and it means that tau xy, where x is bigger than y, f is equal to f. So, but in more details, it means that for every set and every x and y, either they're not elements, but for any x and y, f, okay, so this is hat, f minus x plus y, start again. If it is in the family, then f minus x plus y is also in the family. So, because otherwise we could move it. And we cannot move because you remember it was already there, then we didn't move. So we know this property, but be careful, you could misinterpret this property, so it's not unique. So this is a very important, very heavy property, but it doesn't determine the family. So this 1, 2, 3, 4. Everything is every pair is there. This is shifted because if you try to move, you cannot move. 1, 2, 3, yeah, 6. Okay, but this is also good. No, I don't. The first one, I don't have to. This is also good because what can we move? We cannot. This cannot be x. So we take an x, and we want to move it to a y. Then it's already there, and we cannot do anything else. And there are many in between. Many shifted families are there. And Erdős Corrado used this property to prove it by double induction, K and N. And Peter Frankl found a lemma and a better proof, shorter proof, where only induction on N will be used. So, I don't remember the year, but it was much later, of course. Then if F is shifted, intersecting, and F, G are in F, then F, G is not empty. So my picture, it means, so we know that this is non-empty. So if we have, yeah, so this is 1, 2, 2k minus 1. So they have to meet, but the claim is that they have to meet inside of this starting interval. Proof. Indirect way. Suppose that I will denote this starting interval by t to write less. Suppose FGR in F, but of course I'm speaking about the intersecting shifted family. So, is empty. So it doesn't satisfy the condition. Then if we have many such counterexamples, one minimizing actually, no. Yeah, this is also good, but probably we don't need this. We could speak about minimum of this. It doesn't matter. Wait. Oh, take the minimum of. Not then I correct it later. So F and G are intersecting, but not in T. It means that they look something like this. So, So they are disjoint here, but they are intersecting somewhere here. And so then is not empty, of course, and so it has an element so we have a common element. This is X. And what happens here? Since they have at least one element outside, they can have at most k minus 1 elements inside. So all of it can accept this X. And the same is true for G. So what is covered here is 2k minus 2. So 1 is missing. So there is a y which is not in F and not in G. So, okay, I make it. So there is a, or maybe not, it's not the first one. It's misleading if I write the first one. So there is one which is here, and this is bigger than this number. This is smaller than equal to this number. So x, y is smaller than x. And now apply the transformation for any of them. So take xyg, tau xyg, which is g minus x. So then it will look like this, and because it's shifted, this is also in the family. We cannot change anything by this shift, so it is in the family. So, and now we found F and this family has a smaller intersection because this is lost, and we moved only G to Y, so they are not meeting here, but they stop meeting here. So the size is less than and this is also a counterexample because they don't meet inside. Because, yeah, clear, yeah. Of course, in such proofs, you have to see that it cannot go down to 0, but it's obvious that the intersection cannot be 0 outside if they don't meet inside, because they have k elements. So this is a contradiction. I think this is a Hungarian notation for contradiction. It's not used in other countries. So we proved the lemma. Let me tell a few words about Peter Frank. He was my student, and he started to. He was an excellent student. So when he finished his studies in June. The 5 years, you know, that time it was a diploma, it was not bachelor and master, so 5 years studies, and then finished. In September, he defended his title, candidate of Nauk. So it is a stronger degree than today's PhD, so the more requirements there were. And he started to juggle. He was almost taken to the circus in Budapest because he had with a friend some fantastic performances. But then he went to France, and after some years he moved to Japan, where he became a TV star. So he is not employed by any university. He's working at home, and for some years he wrote maybe one paper per year, but now it's less funny that an old man is juggling, and so he returned to mathematics. He's writing a lot of papers. Do you know Kupavsky, Andrei Kupavsky? Yeah, so they have many joint papers recently. Yeah, so now I am ready to, I have to, instead of chatting, I have to finish the proof. So now let AI be the number of sets of course for all members of the family. Picture might be useful. So this is T. So and the continuation is here. So we take and this has I elements here. So we take all intersections here, and it not necessarily we have all I elements intersections here, only some. And this is the number, how many times we have an I element intersection here. So what we can say, okay, so now the proof is induction on N. Wrong. So now T prime is one more element. So we know that they are intersecting in the first two k minus 1 elements, but it is more used. Then, of course, they have an intersection in the bigger interval, and proof works with 2k. So what are these parts of an F? And two such things must intersect because of the lemma that they are intersecting inside in the first 2k minus 1, so that's in the first 2k. So they are intersecting. So we have here 2k element set, I write it here, a 2k element set, and we choose I element sets in such a way that they are intersecting. So by the induction, it cannot be more than this number. Of course, 2k must be smaller than n, yeah. And so now the size of F I will write the starting point later. So how the sets look like? So they have an I element here for some I, and we can extend this in many ways. So how many ways? We have here n minus 2k elements, and we have to add k minus I. In principle, they all can be chosen. And now, using this, so I cannot be 0, right? Because cannot be 0. It's not important, but no, it cannot be, because if a set is completely here, then it cannot have an intersection with another member inside. So I is from 1, and now substitute it Do you know this rule? If not, then it's easy to prove. So we have n minus 1 element set all together. Here 2k minus 1, and then here n minus 2k. So all together is n minus 1. And question, how many k minus 1 element sets we can choose here. So we choose some, namely I minus 1. It's good that we start from 1. I minus 1 here, and k minus I here. Altogether is k minus 1. And in all possible ways, and independent, so if they are multiplied, and then you get this. So the proof is almost finished. Because there is a small error here. Anybody can see it. The induction. We have a little gap. Sorry? Oh, that's not interesting. It's trivial. K, yeah, so n is, yeah.
I should be, yeah, well,
Yeah, I made here a mistake. It's that they are smaller sets, right? It's on K. So we used this for K also. We want to prove the theorem for K, knowing that it's true for 1, 2, 3, K minus 1. But here we used it for K.
It's trivial because
So we have to prove, because it's a very special case, the size is important. So AK is smaller than 2K minus 1 over K minus 1. This is what we need to prove differently, because we cannot use the induction. And so we have 2K elements, 2K elements, and this is the number of K element sets, so the half sizes. From any pair, only one can be in this modified family. You cannot have both. So it means that it should be at most 1/2 times 2K over K. And it's easy to see that this is the same thing. Again, the Pascal triangle. So if you take this with K, the same, and their sum is this. So now we finish the proof. So what can I do in 6 minutes? I start a new proof, a shorter one, but I will not finish. So now order the elements. Frame 1, 2, 3, n. So usually this is a set, but now the set means around the table. And we consider intervals of length k. And so this is G is an intersecting family of intervals of length k. So it's a very similar problem, but it's much easier because it's linear. So we can have only at most k, at most n such intervals. And lemma is that the size of G is at most k. So again, the best case is when you fix one point and take the k element sets, all k elements as containing this point. And it could be, if we go, I will speak always about moving this direction. So this is, it has the last element, last by 1, and so on, first element, so it's k. It means k pieces. And it is easy to prove because take 1, start with 1k element set. Already trivial that all other ones should start either in this way or that way, so you cannot have more than 2k. But we claim that it cannot be more than k. Why? Because if you take this set and this set, so they are almost meeting, then they cannot meet here because 2k is less than equal to n. So this is why it's important that they are almost meeting here, so they cannot meet here. That means that one of them is not in G. So at most one is in G. So we have this one, we have how many such 2-element intervals? K minus 1. And for any such small interval, we have at most 1. So that is k minus 1 plus the original one is k. So we solved an easy problem similar to the Erdős-Corrado theorem, and we'll continue on Friday. So if you are curious, you have to come.